Welcome, Assalamu alaikum. Today we'll discuss cardinalities of sets. Now, cardinalities of sets basically is an important subject, and this topic would really go a long way if we are able to understand it. Especially its definitions are really very complicated, so we need to really have a nice have a look at it. Now, the cardinality of set is defined as the that we would say that the set cardinality of the set A is equal to the cardinality of set B if the following is true. Number one, the fact that we have a set A and a set B, right? So this is set A, this is the set B, and there is a one-to-one mapping, and it is also onto that nothing here is left. Okay, all the members of A are mapped to the set B, and there is nothing is left here, so which would mean that it is a bijection. So bijection. Now what does bijection mean? It means that we can map every element of the set A to an element of set B, and nothing is left in the set B, and we map only one element to one element. There's no more than one mapping, one to one, only one to one correspondence. So in that case, this would mean that the number of elements in the set A are exactly equal to the number of elements in set B. And if there is one-to-one correspondence, that is an injection, in that case, we would say that the cardinality of the set A is less than or equal to B. Now, if it is one-to-one, it would mean that we can map every element of A to B, but there are some might be left outside. Some elements might be left in B, but they have some element of B might have been left in the case of injection. But still, all the elements of A are catered and they are mapped to one element B, which would mean that the number of elements in the set B are greater than the number of elements in the set A. So in that case, we write that the cardinality of A is less than or the same as the cardinality of B. Okay, so this is how we write it. So when A is less than or equal to B and A is B have different cardinality, we say that the cardinality of A is less than the cardinality of say A. Now, if in this case we have different if they have different cardinalities, then we have a stricter case where we say that this A cardinality of A is less than cardinality of B. Now, as cardinality, a set that is either finite or has the same set cardinality as the set of positive integers is called a countable set. Now, in the case of countable sets, we say that the set A should have either finite, which means there are elements that there's a limit to them, and or they have a cardinality that is the set of integers. We say that we are able to count them. And if that is not true, then we say that the set is uncountable. So for example, the set of real numbers is uncountable. When an infinite set is countable or countably infinite, we say that its cardinality is aleph, right? So aleph naught is the cardinality. It is the first alphabet of the Hebrew alphabet, first letter of the Hebrew alphabet, and we write that the set of cardinality is equal to aleph naught or aleph null. So in this case, if it is countably infinite, now what is countably infinite? So an infinite set is countable if and if it is possible to list the elements of the set in a sequence. For example, they can be indexed by the positive integers. Now, if you remember, we had said that a sequence could be started from 0 to 1, and it could also be started from 1. And for every number, we have a mapping, for example, 0, 1, 2, 3, and it continues. And then we say, let's map them to elements of the set. So if we are able to do this, and we continue doing this, so no matter how many elements appear, we are still able to find a positive number to map them. So if there is 1 lakh elements, we can say, okay, we'll map them to 1 lakh elements. And if there is another element, then we can have 1 lakh plus 1, which would be 100,001. Or maybe if there are million elements, we can say there are 1 million elements. We can still map them with 1 million positive integers. So the reason for this is that one-to-one correspondence f from the set of positive integers to a set can be expressed in terms of a sequence. So a1, a2, a3, an, a1 is equal to f1, a2 is equal to f2, and an is equal to fn. So this is how you describe the countable sets. Now let's look at the example of Hilbert's Grand Hotel. Now Hilbert's Grand Hotel has a countably infinite number of rooms, and each of the rooms have been occupied by somebody, and we can always accommodate a new guest in this hotel. Now how do we do that? For example, there are 1, 2, and finite rooms. So if a new guest comes in, what will we do? We'll tell him, okay, go to the infinite plus 1 room. How will he find the infinite room? He can't do that. So what we can do is we can list the rooms as 1, 2, 3, 4, and so on and so forth. Whenever a new guest arrives, we move the guest 1 to the next room. We say, okay, please go to the next room. That person goes to the next room, and we ask this person in the second room to go to the third room, the person in the third to the fourth room, and so on. And ultimately, everybody has shifted 1 room, and then there's a place for the new guest in the first room, so that we can accommodate it. So this frees up room 1, and which we assign to the new guest, and all the rooms, current guests still have rooms. The hotel can accommodate a countable number of new guests, and all the guests on the countable number of. Similarly, there's a bus as well. So there's a parallel example of a bus as well. Or so showing that a set is countable, we map from 1 to 1, 1 to 2, 2 to 2, 3, 4, 5, 6, 7. So you map 1 to 2, 2 to 4, 4, 3 to 6. So the f is a bijection from the number, natural numbers, to E, which is the set of even numbers, positive even numbers. So they are also countable. So we can keep on counting them until we reach some place. Now, what about rational numbers? Are they countable? Well, the rational numbers are defined as any number which can be expressed as two integers, a ratio of two integers, p over q, such that q is not equal to 0. For example, 3 by 4 is a rational number, while under root 2 is not a rational number. So how do we show that a positive number count? The solution is like this. You can arrange the sequence in a sequence. So this is how we do it. So what we do is we start from the first row. We write 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we keep on going to infinity. And then we divide them by 1, 1, 1, 1, 1, 1. The second row we divide by 2, 2, 2, 2, 2. The third row we divide by 3, 3, 3, 3, and 4, 4, 4, 4, and so on and so forth. But when we start counting them, this is how we count them. We count the first here, and the second one is this. And then we go here, and then we go here, follow the arrows like this. We say this is the first one, this is 2, this is 3, this is 4, 5, and so on. So we can continue counting them, and we can continue counting them, and no matter how far we go, we can still map them to a positive number. So therefore we can say that the set of positive rational numbers are countable, right? So this is a good example of how we can count positive rational numbers. So this is how we can list them down as well. So this is the listing of the rational numbers. So therefore the positive rational numbers are countable. This is called uh, Cantor 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 Cantor. This is called Cantor diagonalization. So now let's look at the strings. Show that the set of finite strings over a finite alphabet is a countably infinite, right? So show that the strings can be listed in a sequence. So all the strings of the length 0 in alphabetical order, and then all the strings of length 1 in lexicographical order, which is the order if we write them in the dictionary, right? So this is how we write them in the dictionary. This is how we write them in the dictionary. So we keep on adding. Now this implies that a bijection from n to s, and hence it is a countably infinite set, right? So we keep on adding strings. Now the next thing is the set of all Java programs is countable. We can do that as well. So this is the Greg counter we were talking about. Now we prove that the set of real numbers is uncountable, right? How is that possible? So suppose what we do is we say that okay, we'll just prove it by contradiction. We'll assume that the set of real numbers is countable. Then the real number between 0 and 1 are also countable, right? So if they are countable, what we can do is we can write the real numbers in the order R1, R2, R3, and we can continue writing them like this. And every number would be, let the decimal representation of this be a listing like this: 0, D11, D12, D13, D14, D5. So these are the digits. This is the digit first, second, third, fourth, fifth, sixth of the first number, and then so on, so forth. We write all of them. Now we can form a real number, a new real number, which can be equal to a real number with the decimal expansion Ri is equal to 3 if Tii is not equal to 3, and Ri is equal to 4, that is Tii is equal to 3, right? So what we do is if this one is equal to 3, then uh, right, we'll use 3, and if this is not equal to, this is equal to 3, then we'll say Ri would be 4. So we look at all these digits, the diagonal digits, and if they are equal to 3, then we'll write, if they are not equal to 3, we'll write it as 3, and if they are equal to 3, we'll write them equal to 4. So now R is not, the new number R is not equal to any of these. because if there was a 3 in there somewhere, right, then it would have been flipped to 4. And if there was a 4 anywhere, if there isn't any 3, then it would be equal to 3. So what will happen is that if there is a real number between 0 and 1 that is not in the list, since every real number has a unit essence, hence all the real numbers between 0, so they cannot be, so we cannot list the set of real numbers, and therefore this is a new real number which is not part of the list, which we had claimed that we have counted all the possible numbers between 0 and 1 and given their decimal expansion. But since we are able to do this, therefore the set of whatever we have assumed that R is countable, that is not correct. Therefore the set of real numbers is uncountable. Okay. So that is it from the cardinality. So let's see.